Hi everyone, welcome to the first mini lesson in the online component of Physics 413. We're going to talk about how to extend our ideas about the canonical partition function tool to composite systems where the components are distinguishable. That's an important concept. Obviously we want to always have composite systems because we're thinking about many particles. But the question of are the components of a system distinguishable or indistinguishable is subtle and the topic of the next two mini lectures. So this will start in chapter 6, section 6 of Schroeder. Make sure you pay attention to that, it'll help a lot. So let's review canonical partition function for a two-level subsystem in equilibrium with a reservoir at temperature T. So we remember our basic setup for the canonical ensemble is that we assume we have a very large reservoir that's in thermal equilibrium with our subsystem, and that we know the quantum energy levels of the subsystem. And so in this example, we're considering two levels. You should know this example like the back of your hand. It really gives you the core of everything you need for chapter 6. So we've got a ground state with energy referenced as 0, and the first excited state with an energy we call epsilon. So the partition function consists of a sum over all the possible Boltzmann factors for this system. And it's important that we've sort of implicitly assumed already that we're thinking about occupying each level with one single particle. So the first term in the partition function is e to the minus beta 0, where we imagine that the particle in the subsystem is occupying the ground state with energy 0. And then the second term in the partition function is the situation where we now imagine the ground state is empty and the one particle that's in the subsystem is occupying the excited state. So this single particle partition function, if you want to call it that, is 1 plus e to the minus beta epsilon. So this is the sum over all possible Boltzmann factors, and the implicit assumption is that only one particle is able to occupy the energy levels. So today's lesson is where we ask about what happens if we allow more than one particle to occupy the energy levels. So what if we have two particles in the subsystem? That's a composite system. And we'll assume that the particles don't interact with each other, and so you can just place them in the E sub s levels without changing the levels at all due to interparticle interactions. It's an important assumption, but it's also one that doesn't restrict us very much. Very often we can find non-interacting or approximately non-interacting circumstances in nature. So we're also assuming that the particles are distinguishable, and that means that it's physically reasonable for us to think about tagging them with some kind of label. And in these slides I'm going to use just a color as my label, so one particle will be red and the other will be purple. That's purely imaginary. It's just a conceptual tag, but there is a question about whether that's physically reasonable. In these slides today, we assume that it is physically reasonable. We'll talk next time about cases when it is not. So, distinguishable non-interacting particles, if we've got two of them in a two-level system, I've just drawn out the energy level diagram for every possible thing we can do with that setup. So we can put both particles in the ground state, we can put purple in the ground, red in the excited, red in the ground, purple in the excited, and then we could put both of them in the excited state. And that exhausts all the possible configurations of this composite system. So let's do the partition function for this composite system now. So we're going to do the same game. We're going to write the Boltzmann factor associated to each of our possible energy level diagrams. So in the first one we've got e to the minus beta 0 because both are in the ground state. The second one we get e to the minus beta epsilon, which is just coming from the epsilon energy of the red particle in the excited state. And we get the exact same Boltzmann factor when the purple and the red are switched, But that's not redundant in this circumstance, right? Even though these Boltzmann factors for these two diagrams are the same, they still need to be added together in the distinguishable composite partition function. That's important to think about. And then finally, when we put them both up here, we get a total energy of 2 epsilon, and so we get a Boltzmann factor e to the minus 2 beta epsilon. So we add all that up, we get Z2, where the 2 says we've got a composite system with 2 particles, the subscript here. We get 1 plus 2 e to the minus beta epsilon plus e to the minus 2 beta epsilon. And if you stare at that for long enough, you'll probably start to see that that is exactly 1 plus e to the minus beta epsilon, quantity squared. So in other words, you take the Z1 that we already knew about from our last lectures and just raise it to the power of the number of particles. So that's pretty cool. And so what we're going to show next is that that idea does generalize to an n particle composite system. So the basic idea is we're going to show that Z sub n, the composite partition function for an n particle system, is the Z sub 1 that you get by thinking about one particle just raised all to the nth power. What I'm doing on this slide is a generalization of the analysis that Schroeder carries out in section 6.6. So I'm going to try to use essentially his notation. If you can understand what he does in section 6.6, you understand this. I'm just elaborating the notation a little bit to make it clear how it generalizes. Important point. The total energy of the composite system is just the sum of all the individual energies of the particles. So the ith particle has energy E sub I and is in level S sub I. Okay? It's important that this is essentially the definition of non-interacting. Non-interacting is not the same as distinguishable, by the way. Non-interacting means when you put a bunch of particles into the levels, they don't talk to each other. In other words, they don't change the levels by their very presence. So if you have a particle in one energy level, it doesn't change any of the other energy levels. And so you can just add them up without worrying that they would change one another by interactions. All right, so this is actually really quite important. If you do have an interacting system, this simple sum will not be true, and you'll lose a lot of important results. So the composite partition function for the n particle system means we have to sum over all the possible states. So we have to sum over all the possible states for particle 1, right? S sub 1 means particle 1 occupying possible states S sub 1. Particle 2 occupying possible states S sub 2. Sum over all the possibilities, the Boltzmann factor of this total energy for the composite system. So the nice thing is that because we have a simple sum in the exponential, we can break it down into a product, right? So e to the x plus y is equal to e to the x times e to the y. And so the composite partition function is the sum over all the possible s sub i's. That's a multiple sum right there of the product of e to the minus beta, e sub 1 of s sub 1, etc., all the way to e sub n of s sub n. And so if you stare at this, I hope you can see that each of these sums, when applied to its appropriate Boltzmann factor, will give the exact same number, and that number will just be z sub 1. So in some sense, the s sub 1, s sub 2, all the way to s sub n, each s sub I is almost like a dummy variable. When you're summing over it, it doesn't matter that it started out referring to particle 1. By the end, when you've summed over all the possible levels, you'll get the same number, z sub 1. And so this is a direct proof. You've got all these products, and each one, when you've done the sum, will give you a z sub 1. And so that gives you the fact that z sub n is equal to z sub 1 raised to the nth power. So this is a specific result, the composite partition function for n distinguishable, non-interacting particles. Here's an example that you should do by yourself on your own paper to see if you've been following along with what I'm talking about in these slides. I would like you to consider a two-level system with n equals 3 distinguishable, non-interacting particles. It's almost always going to be non-interacting in this class. So I want you to draw all the diagrams and write out the associated Boltzmann factor for each diagram to prove by brute force that z sub 3 is equal to 1 plus e to the minus beta epsilon to the third power. And pay attention to whether you can see the pattern that's arising. And to see what I mean, you might want to take a look at Pascal's triangle, which is a mnemonic device for remembering the coefficients of terms in a polynomial expansion of 1 plus x to the nth power, right? And so you can, if you look at the Pascal's triangle, start to connect the numbers that appear in the triangle to groupings of energy level diagrams associated to the two-level system. So I think that's pretty neat, a sort of graphical way to look at the combinatorics of this system. I'm hoping this is straightforward. If you find that this is not straightforward for you to do, that might be a topic that you would consider discussing with me either by email or in some of our online office hours if you can find the time. So one thing I want to point out as you're doing the system with n equals 3 distinguishable particles, we are not talking at all about Pauli exclusion. So it is possible to have all three particles in the same quantum level. I did not tell you whether these were fermions or bosons. In fact, we're not thinking about that kind of quantum statistics at all yet. We will do that in chapter 7, but you actually can't do it. You can't do it in a simple way just with the canonical picture that we've developed. So we are not doing quantum statistics. We're not thinking about Pauli. Any level occupation is allowed. Jeez. So, hopefully this video wasn't too long. Hopefully it wasn't too short. Try this example for yourself, and I hope you'll talk with me about it if you have questions. So we'll see you in the next video.